So we're still under the application of the conservation laws, and in the previous example, we covered quick flow, which is an application of the continuity and the momentum equation. The second and famous example on how to use the continuity and momentum equation to find the fluid flow field or the flow field between two parallel plates is Poiseuille flow. Poiseuille flow is simply a flow between two parallel plates. So we have two parallel plates separated by a distance h, very similar to what we had with the quick flow. The lower plate is fixed, but also the upper plate is fixed, which means that there is no way you can drag one of these two plates to drive the flow or initiate the flow between the two plates. Actually, this is for symmetry, we're going to call that 2h here. So they are separated by distance. We're going to call that distance 2h. So it's a steady, incompressible flow between two parallel plates separated by distance. Steady, incompressible flow between two parallel plates. But in this case, the fluid is driven externally. So there is a source of that fluid here, which means that there is a driving pressure. There is a high pressure here, there is a low pressure here, and that pressure difference is driving that flow between the two plates. I will mark the center line between these two plates is at the middle, and we will measure the y coordinate from here. So this is y equal h, and this is y equal minus h, and this is explain why I picked up the separation distance by 2h to take advantage of the symmetry here, symmetrical boundary condition. So again, I would like to find that velocity distribution. Remember, we're still keeping the no slip condition. Which means that I know that velocity for sure here is 0. Velocity here is also 0 for that for these two specific layers of fluid intact toward the solid surface. So then the velocity is going to be distributed somehow in between. Let's see how to use the continuity and the momentum equation. What are the assumptions? Again, we are solving one-dimension flow. It's all in that direction, and because it's steady, nothing changed relative to the time. It's incompressible. Rho is actually constant, and again, we're going to assume that mu is constant as well into that problem. So let's start with the continuity equation, like what we did in the quick flow. For one-dimension case, I would have partial rho by partial t plus partial rho u by partial x plus partial rho v by partial y plus partial rho w by partial z. It's equal to 0. Simplify. This is 0 either for steady or constant density here. We are solving one dimension. These two goes away for one dimension. Then I'm going to end up having partial rho u by partial x equal 0. Rho will come out for the incompressible flow, and I will end up having this equation here. Rho cannot be 0. This means that partial u by partial x equals 0, which indicate that we are in fully developed flow. You guys remember when we discussed the difference between steady flow and uniform flow? Steady flow means that at any given location, your velocity is not going to change with time. While uniform flow, that means if you pick up a particle, the velocity will not change with position, right? In this situation here, we're going to assume each one of these layers as well has a non-changeable fluid velocity, which means that the particle here will keep that velocity as it goes from one location to the other, which means that this fluid here is uniform. And I'm just explaining that because some books actually said it's uniform, steady, one-dimensional incompressible flow. And I'm just explaining what is the added value when I mention uniform. Uniform means that velocity does not change relative to the position. So this particle here will keep the same velocity along the whole line, streamline to the other side. So again, going back to the governing equation, we concluded from the continuity equation that we really have not only uniform, but we have uniform, fully developed flow between the two plates. Let's jump into the momentum equation. Like what we did with squid flow, we are solving for one-dimension problem here. So I'm going to write the momentum equation in the x direction. So that's the x direction. The momentum equation is partial rho u by partial time t plus u partial rho u by partial x plus v partial rho u by partial y plus w partial rho u by partial z equal minus partial p by partial x plus again, it's partial by partial x for mu, partial u by partial x, plus partial by partial y, mu, partial u by partial y, plus partial by partial z, it's mu, partial u by partial z, plus the gravity force in the x direction. Again, this is cancel out. This is 0 for a steady state. Rho can get out from all the equation, mu can get out of the equation. This is 0. We are solving one-dimension problem. So for one dimension, v and w is 0. This will end up having partial u by partial x, which is coming 0 from the continuity equation, right? Now mu is constant, can get out. So I'm going to end up having here. So left-hand side is 0 minus partial p by partial x plus mu partial 2u by partial x squared plus partial 2u by partial y squared plus partial 2u by partial z squared plus gravity force would be also neglected. So that's the ending right-hand side here. Again, partial u by partial x is 0, so the second derivative is also 0. Velocity change in the y direction, so that's cannot ignore that part. And z partial u by partial z equals 0 because we are solving one-dimension problem. So the final equation that I'm going to get from that momentum equation is partial section mu partial 2u by partial y squared. That's the term here, the viscous effect equal to, this term is not going to be 0 because now I have an external driving force. I cannot ignore that one. So that's going to be partial p by partial x. So in a simple writing, partial 2u by partial y squared equal 1 over mu partial p by partial x. And this is what we got from the momentum equation. You recall what we got from quick flow. Quick flow, the right-hand side was 0 because the pressure gradient in the x direction was 0 because there was no external driving force. There was no delta p here to cause that pressure drop. And when I say partial p by partial x, is the change of the pressure as you go along the x direction, which is mainly the pressure decrease as you go into that direction, mainly by friction. That's what we meant. So this is the equation I need to solve. I have to solve that equation to get u as a function of y. So it's very obvious here that we have to do double integration, use a boundary condition to be able to get that velocity distribution. So partial 2u by partial y squared equal 1 over mu partial p by partial x. So again, we have a flow over a flat surface here. I'm just explaining here. So you have a high pressure in this side, you have a low pressure in this side. Then we will have the boundary layer formed somehow. Then we have the velocity distribution, right? And what's happening to the pressure as you go into that? This is the x direction here. So we know that partial P by partial X, which is a pressure change along the x direction, is exists, right? For that pressure difference here. What's happening to this value? Do you believe that value is positive or negative here? As x increase, what's happening to the pressure in that direction? It's decreased. So we know that partial P by partial X has to be less than 0. It's going to be negative. So if I told you that I'm losing 5 Pascal, for example, if I told you that I'm losing 5 Pascal per meter, so every 1 meter, I have a pressure drop of 5 Pascal due to friction. This means that partial P by partial X is negative 5. Okay? We don't give the value of the pressure gradient in the x direction due to friction loss by a negative value. We give you the value, but you should know in that situation it has to be negative. Okay? That's a first situation. A second situation, let's assume that somehow you were driving a flow against the pressure increase. Suddenly you decided to increase that pressure by any other external means, and you end up having this side pressure is higher than this pressure. So I start with high pressure here, low pressure here. I start driving the flow. While the flow is going in that direction, I start building up a pressure in this side to a moment that pressure here is higher than this pressure here. I have a pH here and P low in here. Initially, the flow is going this way, and this is your velocity distribution, right? At certain moment when both pressures are almost equal, you will find that your velocity distribution looks like this. For certain time. So it's telling me that really there is no change in the pressure here. So partial P by partial X equals 0. But as time goes on, because you are building a high pressure here, you will start reversing the flow of some of the fluid layers near the wall. You'll find that your velocity distribution start doing the following. And you got what we call the reverse flow here. This indicating that partial P by partial X is greater than 0, which means that with increasing X, your pressure also increases. Again, in normal flow condition, we drive the flow from high pressure to low pressure, you got that velocity distribution. Assume under certain circumstances, that pressure start to build up. At a certain moment, both pressures will be equal while the flow is still going in that direction by inertia, by the gained energy initially. Then when start building up the pressure here, maybe you reach a moment where that delta P is equal 0. So you'll find that velocity distribution near the wall is nothing. It's the flow is stagnant here. So this means that between these two locations, the pressure does not change. So partial P by partial X is negative. Then as the pressure keep building up, the value of the pressure in this side will be higher than the pressure in this side. You will start actually reversing the flow near the wall because of that pressure difference here, and you get what we call the reverse flow. In this situation, the pressure between these 2 points is actually greater than 0. Pressure increase from that location to this location. So in that situation here, we can write that partial P by partial X is greater than or equal to 0. Equals 0 when the pressure balance between the two driving sides, and it's not being positive when you get the reverse flow near the wall. So keep that in mind. This is a very important condition. So going back to the momentum equation here. I would like to integrate both equations. So the integration of partial 2u partial y squared equal to the integration of 1 over mu partial P by partial X. Then you integrate, you're going to get partial u by partial y equal to 1 over mu. Now I want to integrate partial P by partial X. Then I have to add C1, right? So now we have to deal with that pressure gradient, okay? If we are dealing with just a friction loss at the wall surface, right? This is, by the way, could be less than or equal 0, right? In very similar to that situation here. So we would like to look to the variation of the pressure along the x direction, right? Are we driving with negative pressure gradient or positive pressure gradient? If we just consider for just friction, and we call that the skin friction, we can assume that the pressure loss is consistent along the surface of that solid surface. So between the two paraplate, either at the lower plate or the upper plate, if it's only considered for the friction loss, nothing else, just the friction loss, we can actually assume that partial P by partial X, it's changing constantly along that line. So for just friction, we can assume partial P by partial X is equal constant. And this is the simplest assumption. Otherwise, you have to give me other function there. So we're going to assume that, oh, we are losing 5 Pascal per meter as we go. So it's not going to change. It's always constant. But it's not going to be 5 Pascal per meter for the first portion, then 3 Pascal per meter in the second one. No, we're gonna say that rate of a change is constant, right? So which means that I can take this guy out of the integration here. So partial U by partial Y is simply 1 over mu partial P by partial X, which is constant, plus C1. Sorry, that has to be, we didn't integrate yet. Oh, that's Y here. So I'm integrating second derivative. This will give me Y, right? Partial P by partial X will get out, so I'm going to end up having Y here, plus C1. I will integrate for the second time. U will come out as a function of Y. It will be 1 over mu partial P by partial X, which has a constant value. Integrating Y is going to be Y squared over 2 plus C1 Y plus C2. And the first impression I'm getting here, that velocity change in a parabolic format here, second order, right? Remember, between the two plates, we assume that center line is in the middle. So Y equal 0 here, Y equal H in here, Y equal minus H in here. We know that velocity is 0 at the top, velocity is 0 at the bottom here, okay? Because of the non-slip condition that we assumed at the beginning. So let's do the boundary condition, and we apply the boundary condition, right? So it's clear, and the most easy one to use is at Y equal H, right? I got U at H equal to 0, and at Y equal minus H, U at that location is also equal 0. Again, this is the non-slip condition. Okay, so let's go back to this equation and apply with the boundary condition. If I put this U equals 0 for the first condition, I will have 0 equal 1 over 2 mu partial P by partial X. Now Y has to be H, so it's going to be H squared plus C1 H plus C2. Use a second boundary condition in the same main equation here. I'm going to have 0 as well, 1 over 2 mu partial P by partial X. Now Y is equal minus H, so this will be minus H squared plus C1 times minus H plus C2. This is going to be squared, so it's going to be the same as this term. So I'm going to end up having minus in here, plus in here. I need to solve the two equations together, so I can actually get C1 and C2. So I'm having 0 equal 1 over 2 mu partial P by partial X H squared plus C1 H plus C2. The second equation will be 1 over 2 mu partial P by partial X. Again, it's still H squared minus C1H plus C2. Let's subtract equation 1 minus 2. This is equation 1. This is equation 2. If you subtract equation 1 minus 2, left-hand side is 0. This term will cancel out. C1H minus C1H. So I'm going to have 2 C1H. Then C2 will cancel out. This will lead me to that C1 is actually equal 0. You take C1, go back to any one of the equations to get C2. Anyone, it doesn't matter. I'll go to the second equation. So C2 will actually equal 1 minus 1 over 2 mu partial P by partial X H squared. You got C1, got C2. Now you can complete the velocity profile. U as a function of y is equal to 1 over 2 mu partial P by partial X y squared plus C1 is 0 plus C2, which is minus 1 over 2 mu partial P by partial X H squared. Let's simplify the equation a little bit. If you simplify the equation, you will find that u as a function of y is equal to, let's take minus 1 over 2 mu partial P by partial X as constant. Let's take actually H squared as well out. So what you're going to get, I will get, if you take minus H squared over 2 mu partial P by partial X, this will give you 1. But this will give you minus y over h to the square. And this is the equation for the velocity distribution. If you plot this velocity distribution for a given value of partial P by partial X, you will find a very famous parabola distribution for the velocity between the two fixed plates. If you put y equals 0, this will be, if you put y equal h, right? This is the upper boundary condition. H over h is 1, 1 minus 1 is 0, velocity would be 0. If you put y equal minus h over h is minus 1 square will give me 1. 1 minus 1 is going to give me 0, so the velocity is 0. Then if you put y equals 0, what are you going to get? This term goes away, right? And I'm going to end up having minus u at y equal 0 equal minus h squared over 2 mu partial P by partial X. And this is at the center line. And this is simply as your maximum velocity. Because if you plot that profile, this is what you're going to get. This is your U max. You end up having 0 at the upper plate and 0 at the lower plate. Then the velocity decrease from the max value at the center line all the way to that 0. That's a velocity distribution, and this is the maximum velocity. Now the question is, how can I have a maximum velocity of negative value? Said, no, because we agreed that partial P by partial X has to be negative in the direction of flow. If this is the high pressure, this is your low pressure, so you're going to lose pressure as you go into the X direction. So partial P by partial X is going to be negative, which end up to give you a positive value of velocity. So keep in mind that partial P by partial X in that direction of flow is negative unless it is mentioned that we have different situation. But by default, partial P by partial X is negative in the flow direction when the flow is driven from high pressure value to a low pressure value. And again, that pressure drop is coming because of the skin friction. So that's simply, again, how to use the continuity and momentum equation to do an analytical solution for a fluid flow between two better plates. In the first case, quick flow, one was fixed, the other one was moving, the upper one was moving. And in the Poiseuille flow, the two plates are actually fixed, and there was a pressure gradient included here. We can play with these two very famous examples here. So, for example, in quick flow, what if I told you that the lower plate is moving, but the upper one is not? What if I told you that both plates are moving, but with different velocity? It's all what we play with is actually changing the boundary conditions. But the the simplification of the continuity and momentum equation. The end up formula is the same, then the procedure will be the same, but for sure, the velocity profile will change based on that boundary condition. So keep that in mind. If the boundary condition changed a little bit, it's not going to impact the overall process of solving analytically here, but you end up having different velocity profile. And you will experience that more in maybe more practice problems or other situation. So let's conclude that Poiseuille flow and the use of the conservation laws to solve that flow distribution.